Now in the previous session we have already understood what is buckling analysis, what are the outputs that we are going to calculate from the buckling analysis. There are certain points that we need to remember when we are performing buckling analysis, so we have understood that also. Now we are going to solve a problem and understand how to perform the buckling analysis in Ansys Workbench. So for understanding this, we will take the first problem, that is, it is a stepped rod and it is fixed at one end as shown in the figure, and it is actually loaded by two forces. You can see two forces that are acting over here. One force is acting on the top, which is 1000 newtons, and it is acting in the axial tensile direction, and there is one more load which is acting at this position of 2000 newton, but it is acting in the axial compressive direction. Okay, and we are supposed to find out the buckling load for this particular design. The material that we are going to use for this analysis is structural steel. The large diameter over here is 0.011982. Small diameter is 0.010, and the length of the large diameter is 0.2 meters, and the length of the small diameter is 0.1 meters. So let us perform this analysis in Ansys Workbench. So I will come into Ansys Workbench. Now, if you remember, we discussed one point in points to remember, that is, a buckling analysis, a linear buckling analysis should always be performed after the static structural analysis. So first we are going to perform a static structural analysis, okay, and I will say linear buckling analysis. And then the material that we are going to use for this example is structural steel. So that is the same material that we get by default, so I don't need to enter into the engineering data. And then I'm going to come into the geometry, and then we will create the geometry. So let us create the geometry first. So as we can see over here, the unit system is into meter. I'll take one sketching plane and let us start sketching. So I'll draw one circle, and then we will give the dimensions for this. So the dimension is 0.011982. 0.011982. 0.011982. So that is the diameter that we've got. Okay, so this is the model that we've got, okay, whose diameter has been mentioned. Now let us come back to the modeling and we will extrude this. So this is the sketch that we need to extrude, and the unit, the length of this is 0.2 meters. So I will enter this as 0.2 meters and we will generate it. So this is the model that we got. Similarly, now I need to sketch another model on this face. We will enter into the sketching tab, and again over here I am going to draw one circle whose diameter is 0.010. 0.010. And then we are going to extrude this to a depth of 0.1 meter. Now because both the step bars have the same material, I will use the add material option. If both of them had different materials, we will have to do it as add frozen, but now I will make it as add material. Okay, so this is the geometry that we have. Okay, so now the geometry is ready. After this, we will enter into the mechanical window. Okay, now once we are here in the mechanical window, the first thing is to check the material, and then we will mesh the model. So I am going to use the default mesh settings. Okay, we can observe over here that we've got tetrahedral elements. Okay, if you wish, you can add the proximity and curvature option so that we get finer meshing over here. Okay, now you can see over here that this region has been meshed very fine. Okay, after this, now we will apply the boundary conditions. So I'll take the static structural node and we will apply one fixed support on this end as mentioned in the problem, and at this particular end there is an axial tensile force of 1000 newtons. So I'm going to apply a force of 1000 newton in a tensile direction, and there is another force at this face which is 2000 newton, but it is in the opposite direction, a compressive load. Okay, so these are the loading conditions that we've applied: fixed support, tensile load of 1000 newton, compressive load of 2000 newton. Okay, and then I will just add one deformation option over here and we will solve the analysis. Okay. Now once we get the solution, you can check the result. Okay, and then we will exit from the static structural analysis. Now the static structural analysis has been performed, but we are interested into the buckling load. So now what we are going to do is we will add one linear buckling analysis system to the solution of the static structural analysis. So you can select it from the toolbox and drag it to the solution. Okay, this is very important. Left click, use your left mouse button to click, keep your left mouse button pressed and drag it to the solutions cell of the static structural analysis system and drop it there. Once you drop it, you will see the engineering data, geometry, model and the entire setup and solution has been shared with the linear buckling analysis. And now we will enter into the setup cell of the linear buckling analysis system. Once you come over here, you can see that the meshing static structural data, the loads, the solution has been taken, and in linear buckling analysis system, here you can see that it is pre-stressed. Pre-stressed, that means the stress has been taken from the static structural analysis. Okay, now click on analysis settings, and here as we change the number of modes to find in vibration analysis or modal analysis, similarly even in buckling analysis we need to mention the maximum modes to find. Okay, so here we will say that I only want to find the first buckling load factor, which will be the lowest one. And now we will click on solution node, right click, and we will say solve. So it will solve and it will give the output of a load multiplier. It takes time because of the meshing that we've done. We have used proximity and curvature, because of which we have got a very finer mesh, and due to the same the run time or the analysis time is taken a longer time. Okay. Now when you click on the solution node, here you can see what is the load multiplier. So the load multiplier is 22.967. Okay, so 22.967 multiplied by 2000. So here the load will be 45,934. So at 45,934 newtons, the model will buckle in combination with 22.967 multiplied by 1000. So with the combination of these two loads, the model will buckle. Okay. So this is how you will perform the buckling analysis using the static structural analysis system plus the linear buckling analysis system.